Hello. Today we're going to learn about how a single artificial neuron, called a perceptron, makes decisions. This is one of the fundamental building blocks of neural networks and artificial intelligence. Before we dive into the artificial neuron, let's first understand its inspiration, the biological neuron in our brains. A biological neuron has several key parts: dendrites that receive signals, the cell body that processes them, and an axon that transmits the output signal to other neurons. Now, let's see how this biological neuron inspired the artificial perceptron. An artificial neuron, or perceptron, is a simplified mathematical model that mimics the behavior of a biological neuron. Just like a biological neuron, it receives inputs, processes them, and produces an output. Let's break down how a perceptron works. First, it takes multiple inputs, which could be features from our data. Each input has an associated weight that determines its importance. The perceptron then calculates the weighted sum of these inputs. It also includes a bias term that shifts the decision boundary. Finally, the weighted sum is passed through an activation function to produce the output. Now, let's see how a perceptron can be used for a simple classification task. Imagine we have a dataset with two features, x1 and x2, and we want to classify each point as either belonging to class A or class B. The perceptron will learn a decision boundary that separates these classes. Let's walk through how a perceptron makes a decision step by step using a simple example. Imagine we have a perceptron with two inputs, x1 and x2, with weights w1 equals 2 and w2 equals -1, and a bias of b equals -3. The formula for the weighted sum would be 2 times x1 minus 1 times x2 minus 3. For the activation function, we'll use a simple step function. If the weighted sum is greater than or equal to 0, the output is 1 class A, otherwise the output is 0 class B. Now, let's see how this perceptron classifies some points in our feature space. First, let's find the decision boundary. The weighted sum is 0 at the boundary, so we have 2x1 minus x2 minus 3 equals 0. Solving for x2, we get x2 equals 2x1 minus 3. This gives us a line with slope 2 and y-intercept -3. Let's test a point above this line, say 3, 2. Our weighted sum would be 2 times 3 minus 1 times 2 minus 3, which equals 1, which is greater than 0. So the output is 1 class A. Now, let's test a point below the line, say 1, 0. Our weighted sum would be 2 times 1 minus 1 times 0 minus 3, which equals -1, which is less than 0. So the output is 0, class B. So far, we've been using a simple step function as our activation function. However, modern neural networks often use different activation functions like the sigmoid, ReLU, rectified linear unit, or TAN. The sigmoid function squishes any input into a value between 0 and 1, making it useful for probabilities. ReLU outputs 0 for negative inputs and keeps positive inputs as they are, which helps with faster learning. TAN is similar to sigmoid, but outputs values between -1 and +1. Now, let's briefly discuss how a perceptron learns. Initially, the weights and bias are set to random values. During training, the perceptron makes predictions on training data and compares them to the actual labels. If there's an error, the weights and bias are adjusted to reduce the error. This process continues for many iterations until the perceptron makes accurate predictions or reaches a maximum number of iterations. For a simple perceptron, the weight update rule is W new equals W old plus learning rate times error times input. While a single perceptron is powerful for linear classification tasks, it has limitations. The most famous example is the XOR problem, where a single perceptron cannot correctly classify all points. This is because the XOR pattern isn't linearly separable. You can't draw a single straight line to separate the two classes. To overcome this limitation, we connect multiple perceptrons together to form neural networks, which can learn more complex, non-linear decision boundaries. In summary, a single artificial neuron, or perceptron, works by taking weighted inputs, adding a bias, and applying an activation function to produce an output. While it can classify linearly separable data, it's limited in handling more complex patterns. When combined into neural networks, these simple units become incredibly powerful, enabling the advanced artificial intelligence systems we see today. Thanks for watching.